Alright people, we have our second part of our stoichiometry video here that I wanted to share with you guys. This is for the limiting reactant stuff. Now, I'm going to try to do this fairly quickly for you guys so you don't have a video that is 22 minutes long to watch, but I do want to go through it thoroughly as well. Now, in order to do this, you're going to have a pretty good understanding of what stoichiometry is and how to do stoichiometry problems. So if you haven't watched that video, make sure you go back and do that first. Now, limiting reactant, let's go through the basics first, because those are pretty easy. Students are able to understand what limiting reactants are pretty well. It's a pretty intuitive concept, and we can use a recipe in order to show that. And so we use one that is a recipe we're familiar with, just a sandwich. If we look at the ingredients and what the recipe calls for, we can identify how many sandwiches we can make, and that's what limiting reactant really is. Which of these different ingredients is going to limit how many sandwiches we can produce? That's the maximum number of sandwiches we can make, and then one of these things is going to run out. The other ones we're going to have extra of, and so the one that runs out is that limiting reactant. And so we can go through this pretty easily because they're whole numbers. We can see things. We know the ingredients. This is something that is tangible. We understand. What usually happens is when we take this and turn it into chemistry stuff, students get confused. So let's look at this here real quick and see if we can come up with our answer though. If we have 26 slices of bread, it takes 2 slices of bread, we can make 13 sandwiches. 14 and 1, that makes 14 sandwiches. 30 and 3, that makes 10 sandwiches, right? So if we look at the amount of sandwiches we can make a total of 10 sandwiches. And only 10 sandwiches. We run out of ham. We have extra cheese. We have extra bread. Ham is the limiting reactant. It runs out first. Simple, right? Now, applying this to real chemistry problems, again, is where students kind of struggle. In order to kind of give you a little bit more information here, I want to show you the kind of math that we're going to be doing with chemistry with instead this ham and cheese sandwich. So this is how it looks. We can start with our 26 slices of bread. And we can solve for how many sandwiches we can make. Let's see here, I'm going to do just SD for sandwich. It takes 2 pieces of bread. There's our 13 sandwiches. We can do the same thing with our cheese. We have 14 slices of cheese. For 1 sandwich, it takes 1 piece of cheese. So we get our 14 sandwiches. Same thing for the ham. We have 30 pieces of ham. And 1 sandwich takes 3 pieces of ham because this person likes a lot of ham in their sandwich, so we get 10 sandwich. So this is basically the math that we're going to be doing. You're going to notice that this looks a lot like the mole ratio step. And that's because it is. Let's take the recipe here and write it as a balanced chemical reaction. If we do, the ingredients are our reactants, 1 piece of cheese, and the number that goes into each are our coefficients. Ham produces 1 sandwich. Products, reactants. And then we have our coefficients, just like we do in a chemical reaction. So we have our coefficient ratio here. Here. And the last one here. So there we go. Easy. Let's try a real problem. The combustion of hydrogen gas and oxygen gas forms water vapor according to the balanced chemical reaction below. If we have 5 grams of hydrogen and 20 grams of oxygen, so I'm going to put this down here. I have 5 grams of oxygen. I'm going to choose black. And 25 grams of oxygen. How much water could be produced? And that is going to be in grams as well here, so I did grams here. This is the same thing. The only difference is that we have to first convert our mass of our given reactants into moles. If we go backwards here in step, I'm not going to erase things, but if we go backwards in our process here, we had our different ingredients here as numbers of things, and so our ingredients here need to be numbers of things as well, which is moles. So we take our first thing, 5 grams of hydrogen, and we're going to convert that into moles. 1 mole of hydrogen is 2 grams hydrogen. Same thing down here, 25 grams of oxygen, 1 mole of oxygen is 32 grams of oxygen. That gets us 2.5 moles of hydrogen. And then this one, let's see, 25 divided by 32 is going to get us 0.78 moles of oxygen. We can't stop there. These are our ingredients. And the ingredients don't tell us which one is going to run out first. Just like back here, we had our ingredients, and I'm not going to erase things here, you can still see it. We noticed that our our HAM, we had the greatest amount of HAM, but that's what limited our reaction. Same thing here, we have more oxygen here, but we need to go all the way to our product, all the way to water, to figure out which one is going to run out first. So we go through the next step. 1, 2 moles of hydrogen is 2 moles of oxygen. Again, just like with ham sandwich, those come from the balanced chemical reaction, our mole ratio step. 1 mole of oxygen down here, 2 moles of water up here. Oh, made a mistake. This should be water, right? We're solving for the product, the water. We're looking at how many sandwiches again. I'll keep using that. How many sandwiches can you make? How many sandwiches can you make? So we're looking at water in this case. That's our sandwich. That's our product. So these go away. We end up with 2.5 moles of water here. And 0.78 times 2 divided by 1 is 1.56 moles of water here. This is our smaller amount. This is the fewer number of sandwiches we can make. This is the smaller amount of water we can make. So this is our answer in moles, and that means that oxygen is going to be the limiting reactant. Notice that oxygen started with a much greater mass than the hydrogen, but because of the mole ratio, the molar masses and the mole ratio, it comes out to be the one that produces less water. Now we're not done. The problem asks us to find out how much water we produce, so we have to do one more step and convert it into our grams of water. 18 comes from the periodic table. That gets roughly, I got about 28 grams of water that gets produced. So there's that. This reaction here doesn't tell us anything in terms of the answer. It only tells us which one is the limiting reactant. It tells us that hydrogen is an excess. Oxygen is limiting. We have extra of this. So this is what's going to determine how much water gets produced. If you haven't yet, make sure you go back and write this all down so you have that in your notes as you use it to work on the next problems. Question number 2, I'm going to have you pause the video right now and work through this on your own. Alright, let's say that you unpause it and you have the answer. Our answer is, if you didn't go through that, you are doing it wrong. So let's go through and show you what you should have had to see if you did it correctly. We have copper chloride and sodium nitrate. They go through a double replacement reaction to produce copper 2 nitrate and table salt. The balanced chemical reaction is below. If you're given 15 grams of each, how much salt would be produced? So first of all, I want us to notice that we have lots of chemistry terms here that can kind of get in the way and get us confused. What we need to focus on here is this 15 grams of each. It doesn't matter what is what down here, so the language doesn't need to get too confusing. We have 15 grams of both reactant. It's asking for how much salt is being produced, and we should know that sodium chloride is our salt. Now, for those of you that know a little bit more chemistry than what this is intended to show, copper nitrate is also a salt of sorts, but this is the salt. This is table salt. This is the one that the problem is asking about. So we go through a process. Again, we have to convert into moles. 15 grams of copper chloride. I'm going to convert this guy into moles. Grams of copper chloride is 1 mole of it. And if we go to the periodic table, we find out that it's 134.5 grams of copper chloride in a mole. Those cancel, and that comes out to be 0.111 moles of CuCl2. Next thing down here, we're going to do the same thing with sodium nitrate. 15 grams of sodium nitrate, 1 mole of it, and that's going to be 85 grams. And that one comes out to be, I think, 0.176. Yep, 0.176 moles of NaNO3. Alright, so again, we have our ingredients here. That is not enough. We have to make sandwiches. We have to go to product. We have to figure out how much of those we can make. So let's go through and do this. We have our mole ratio step. 2 moles of NaCl, 1 mole of CuCl2. Same thing here. 2 moles of NaCl is 2 moles of NaNO3. Cancels. 0.222, and I don't know, times 2 is 0.353 moles of NaCl. Moles NaCl. So here again, I want to show you we have the equal masses for both of these. So we can't tell which one limits based on that. And we can't say both of them run out at the same time because they don't. We have 0.11 moles of the copper chloride and 0.176 moles of the sodium nitrate. So here are 2 different ingredients. It looks like we have less here, and we end up having it, which is just, it's coincidental, but we still have to go through to our end result and end up with that amount of sodium chloride that we produced, or the sandwiches. Notice that we have the same thing here, so we're comparing the same product. This is gone now, and we can solve for our mass of salt. 1 mole of NaCl is 50, I forget, does he 23 plus 35.45, so it's 58.5. You end up with about 13 grams of salt. And that's how we would do a problem like this. Remember here, this is the big step right here. You have to go to this step. You must go that far. Oh, now this has got all sorts of messy. Alright, getting rid of this, we got one more problem we're going to do. This is an interesting problem because it's one that my AP chemistry students do at the beginning of the year. And the language here isn't real fantastic, so let me read through it for you and then have you pause the video and go through and see if you can come up with the right answer. So we have aluminum can replace copper. So we have aluminum and we have copper. Ooh. And that copper is going to be in solution right here. The copper chloride is in solution according to the balanced chemical reaction below. This is particularly useful in isolating copper in empirical formula labs. And this is the lab that we do. And you don't need to know the background of the lab. All you need to know is that if we put aluminum wire into a solution of copper chloride, they'll replace each other. We end up with copper at the end, copper metal right here, and aluminum chloride. The problem says if we have 2 grams of copper chloride and 5 grams of aluminum wire, will this be enough? So will this one be in excess? We want this one to run out completely, which tells me that this one should be the limiting reactant. Is this going to be enough? So go ahead and pause the video and work on this problem now. Seriously. Pause the video and work on it. Alright, welcome back. Assuming that you pause it and have gone through this, I'll show you the end result. So we have 5 grams of our aluminum. Convert that into moles. And a mole of aluminum weighs 27 grams. So we end up with 5 divided by 27 gets us 0.185 moles of aluminum. Do the same thing with the copper chloride. We have our 2.0 grams of it. Well, this is the same stuff we had in the last problem too, isn't it? 1 mole CuCl2. That's going to be 134.5 grams of it. Going off of memory here, so hopefully that's correct. 2 divided by 134.5 gets us 0.015 moles of the CuCl2. Although it looks like we're going to have plenty of aluminum, a much bigger number here than this one, we still want to prove this by going all the way to the product. We're going to solve for the product. Now, in the problem, it never says which product to solve for. We have 2 different products, copper and aluminum chloride. It doesn't matter. Just choose one and choose the same one for both of them. So here is my first process here. We have 2 moles of aluminum, 3 moles of copper. Same thing here. I'm going to do the copper again. We have 3 moles copper, and then we have 3 moles of copper chloride. So I do this one quick, 0.015 moles of it. And we get 0.185 times 3 divided by 2, 0.278 moles of copper. We can stop here. We've answered the problem. Yes, we will have plenty of aluminum here because it runs out, or the copper chloride is going to run out way before the aluminum does. We can see that here at this point. This is a limiting reactant here. This is the product we get from the limiting reactant, and we end up then running out of that far beyond this. This is going to be in excess by a significant margin. So the answer is going to be yes. And in any kind of yes or no problem like this, a limiting reactant problem, you need to show your work. You have to go all the way and make sure that you have that. Alright, there we are, guys. There's limiting reactant. Hope you enjoyed it. Make sure that you do these problems and ask questions if you have them. Alright.